Welcome friends. In this chapter, we define and study Gauss' useful notion of congruence for integers. According to Gauss, if a number n measures the difference between two numbers a and b, then a and b are said to be congruent with respect to n, if not incongruent. Definition: let n be a fixed positive integer. Two integers a and b are said to be congruent modulo n if n divides the difference a minus b, that is, provided that a minus b is equal to kn for some integer k, and it is symbolized as follows. Example 1. 13 congruent to 3 mod 5. Since 13 minus 3 is divisible by 5. 18 congruent to 3 mod 5. Since 18 minus 3 is divisible by 5. Similarly, 6 congruent to 6 mod 4. 38 congruent to 6 mod 4, 59 congruent to 10 mod 7, 40 congruent to 1 mod 13. Definition: when n doesn't divide a minus b, we say that a is incongruent to b modulo n, and in this case we written it as follows. Example 2. The following are examples for incongruence. 17 not congruent to 3 mod 5. Since 17 minus 3 is not divisible by 5. 4 not congruent to 2 mod 4, since 4 minus 2 is not divisible by 4. Similarly, 36 not congruent to 6 mod 4, 50 not congruent to 10 mod 7, 41 not congruent to 1 mod 13. Lemma: every integer is congruent modulo n to exactly one of the values 0, 1, 2, etc. n minus 1. In particular, a congruent to 0 mod n if and only if n divides a. Proof: given an integer a, let q and r be its quotient and remainder upon division by n, so that a is equal to qn plus r, where 0 less than or equal to r less than n. Then, by division of congruence, a is congruent to r mod n, because there are n choices for r. We have that every integer is congruent modulo n to exactly one of the values 0, 1, etc. n minus 1. In particular, a congruent to 0 mod n if and only if n divides a. Definition: the set of n integers 0, 1, etc. n minus 1 is called the set of least non-negative residue modulo n. Definition: a collection of n integers 0, 1, etc. n minus 1 is said to form a complete set of residues or a complete set of residues modulo n if every integer is congruent modulo n to one and only one of the ak. Remark: if a1, a2, etc. an is a complete set of residues, then a1, a2, etc. an are congruent modulo n to 0, 1, etc. n minus 1, taking in some order. Example 3. Based on the remark minus 100, minus 12, minus 3, 9, 81 constitute a complete set of residue modulo 5. 4. Minus 100 congruent to 0 mod 5, minus 12 congruent to 3 mod 5, minus 3 congruent to 2 mod 5, 9 congruent to 4 mod 5, 81 congruent to 1 mod 5. Theorem 1. For arbitrary integers a and b, a congruent to b mod n if and only if a and b leave the same non-negative remainder when divided by n. Proof: first take a congruent to b mod n, so that a is equal to b plus kn for some integer k. Upon division by n, b leaves a certain remainder r, that is, b is equal to qn plus r, where 0 less than or equal to r less than n. Therefore, a is equal to b plus kn, which is equal to qn plus r plus kn, which is equal to q plus k into n plus r, which indicates that a has the same remainder as b. On the other hand, suppose we can write a is equal to q1n plus r and b is equal to q2n plus r with the same remainder r, 0 less than or equal to r less than n. Then a minus b is equal to q1n plus r minus q2n plus r, which is equal to q1 minus q2 into n. and hence n divides a minus b. Now, by the definition of congruence, we have a congruent to b mod n. Example 4. Because the integers minus 56 and minus 11 can be expressed in the form minus 56 is equal to minus 7 into 9 plus 7. Minus 11 is equal to minus 2 into 9 plus 7 with the same remainder 7. Theorem 1 tells us that minus 56 is congruent to minus 11 mod 9. Going in the other direction, the congruence minus 31 congruent to 11 mod 7 implies that minus 31 and 11 have the same remainder when divided by 7. This is clear from the relations. Minus 31 is equal to minus 5 into 7 plus 4, 11 is equal to 1 into 7 plus 4. Theorem 2. Let n greater than 1 be fixed and a, b, c, d be arbitrary integers. Then the following properties holds. A congruent to a mod n. B. If a congruent to b mod n, then b congruent to a mod n. C. If a congruent to b mod n and b congruent to c mod n, then a congruent to c mod n. D. If a congruent to b mod n and c congruent to d mod n, then a plus c congruent to b plus d mod n and ac congruent to bd mod n. E. If a congruent to b mod n, then a plus c congruent to b plus c mod n and ac congruent to bc mod n. F. If a congruent to b mod n, then a raised to k congruent to b raised to k mod n for any positive integer k. Proof. For any integer a, we have a minus a is equal to 0 into n, so that a is congruent to a mod n. Now, if a congruent to b mod n, then a minus b is equal to kn for some integer k. Hence, b minus a is equal to minus kn, which is equal to minus k into n. And because minus k is an integer, this yields property B. To prove property C, suppose that a congruent to b mod n and b congruent to c mod n. Then there exist integers h and k satisfying a minus b is equal to hn and b minus c is equal to kn. It follows that a minus c is equal to a minus b plus b minus c, which is equal to hn plus kn, which is equal to h plus k into n, which is a is congruent to c mod n in congruence notation. To prove property D, assume a congruent to b mod n and c congruent to d mod n. Then we are assured that a minus b is equal to k1n and c minus d is equal to k2n for some choices of k1 and k2. Adding these equations, we obtain a plus c minus b plus d is equal to a minus b plus c minus d, which is equal to k1n plus k2n, which is equal to k1 plus k2 into n. Or as a congruent statement, a plus c congruent to b plus d mod n. As regards the second assertion of property D, note that AC is equal to b plus k1n into d plus k2n, which is equal to bd plus bk2 plus dk1 plus k1 k2n into n, because bk2 plus dk1 plus k1 k2n is an integer. This says that AC minus BD is divisible by n, and hence AC congruent to BD mod n. The proof of property E is covered by D and the fact that C congruent to C mod n. Finally, we obtain property F by making an induction argument. The statement certainly holds for k is equal to 1, and we will assume it is true for some fixed k. From D, we know that A is congruent to B mod n and A raised to k is congruent to B raised to k mod n. Together imply that A into A raised to k is congruent to B into B raised to k mod n, or equivalently A raised to k plus 1 is congruent to B raised to k plus 1 mod n. This is the form the statements should take 4k plus 1 and so the induction step is complete. Example 5. Show that 41 divides 2 raised to 20 minus 1. Solution. Since 2 raised to 5 is congruent to minus 9 mod 41, by part F of theorem 2, we have 2 raised to 5 raised to 4 is congruent to minus 9 raised to 4 mod 41. That is, 2 raised to 20 is congruent to 81 into 81 mod 41. But 81 is congruent to minus 1 mod 41. And so, 81 into 81 is congruent to 1 mod 41. Using parts B and E of theorem 2, we finally arrive at 2 raised to 20 minus 1 is congruent to 81 into 81 minus 1, which is congruent to 1 minus 1 congruent to 0 mod 41. Thus, 41 divides 2 raised to 20 minus 1 as desired. Example 6. Find the remainder obtained upon dividing the sum 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial plus etc. plus 99 factorial plus 100 factorial by 12. Solution. We note that 4 factorial is congruent to 24, which is congruent to 0 mod 12. Thus, for k greater than or is equal to 4, k factorial is congruent to 4 factorial into 5 into 6 into etc. into k, which is congruent to 0 into 5 into 6 into etc. into k congruent to 0 mod 12. In this way, we find that 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial plus etc. plus 100 factorial is equal to 1 factorial plus 2 factorial plus 3 factorial plus 0 plus etc. plus 0, which is congruent to 9 mod 12. Accordingly, the sum in question leaves a remainder of 9 when divided by 12. Theorem 3. Let f denote a polynomial with integral coefficients. If a congruent to b mod n, then fa congruent to fb mod m. Proof. We can suppose fx is equal to cn x raised to n plus cn minus 1 x raised to n minus 1 plus etc. plus c0 were the ci are integers. Since a congruent to b mod m, we can apply part E of the above theorem repeatedly to find a square congruent to b square, a cube congruent to b cube, etc. a raised to n congruent to b raised to n mod m. And then Cj a raised to j is congruent to Cj b raised to j mod m. And finally, Cn a raised to n plus Cn minus 1 a raised to n minus 1 plus etc. plus C0 congruent to Cn b raised to n plus Cn minus 1 b raised to n minus 1 plus etc. plus C0 mod m. Theorem 4. If Ca congruent to Cb mod n, then A congruent to B mod m, where D is equal to GCD of Cn. Proof. By hypothesis, we can write C into A minus B is equal to Ca minus Cb, which is equal to Kn for some integer k. Knowing that GCD of Cn is equal to D, there exist relatively prime integers r and s satisfying C is equal to dr, n is equal to ds. When these values are substituted in the displayed equation and the common factor d cancelled, the net result is r into a minus b is equal to ks. Hence, s divides r into a minus b and GCD of rs is equal to 1. Euclid's lemma yields s divides a minus b. Hence, a is congruent to b mod s. As s is equal to n by d, this gives a congruent to b mod n by d. Remark. Theorem says that if Ca congruent to Cb mod n with d is equal to GCD of Cn, then we can divide both sides of the congruence by C to get a congruent to b mod n by d. Attention. In theorem 3, it is unnecessary to stipulate that C incongruent to 0 mod n. Indeed, if C congruent to 0 mod n, then GCD of Cn is equal to n, and the conclusion of the theorem would state that A congruent to B mod 1, that is 1 divides A minus B. which holds trivially for all integers a and b. Example 7. Illustrate that the product of two integers, neither of which is congruent to 0, may turn out to be congruent to 0. Solution. 4 incongruent to 0 mod 12 and 3 incongruent to 0 mod 12, but 4 into 3 congruent to 0 mod 12. The following result follows immediately from Theorem 3. Corollary 1. If CA congruent to CB mod n and GCD of Cn is equal to 1, then A congruent to B mod n. Example 8. Consider the congruence minus 35 congruent to 45 mod 8. It can be written as 5 into minus 7 congruent to 5 into 9 mod 8. The integers 5 and 8 being relatively prime, we may cancel the factor 5 to obtain a correct congruence minus 7 congruent to 9 mod 8. The following results follows immediately from Corollary 1. Results. If AB congruent to 0 mod n and GCD of AN is equal to 1, then B congruent to 0 mod n. If AB congruent to 0 mod P with P A prime, then either A congruent to 0 mod P or B congruent to 0 mod P. Corollary 2. If CA congruent to CB mod P and P does not divide C where P is a prime number, then A congruent to B mod P. Proof. The conditions P does not divide C and P A prime imply that GCD of C P is equal to 1. Hence, the result follows from Corollary 1. Binary and decimal representation of integers. Lemma. Given an integer b greater than 1, then a positive integer n can be written uniquely in terms of powers of b as n is equal to am b raised to m plus am minus 1 b raised to m minus 1 plus etc. plus a2 b raised to 2 plus a1 b plus a0, where the coefficient ak can take on b different values 0, 1, etc. b minus 1. Proof. The division algorithm yields integers q1 and a0 satisfying n is equal to q1b plus a0, 0 less than or equal to a0 less than b. If q1 greater than or equal to b, we can divide once more, obtaining q1 is equal to q2b plus a1, 0 less than or equal to a1 less than or equal to b. Now substitute for q1 in the earlier equation to get n is equal to q2b plus a1 into b plus a0, which is equal to q2b square plus a1b plus a0. As long as q2 greater than or equal to b, we can continue in the same fashion. Going one more step, q2 is equal to q3b plus a2, where 0 less than or equal to a2 less than b. Hence, n is equal to q3 b raised to 3 plus a2 b raised to 2 plus a1b plus a0, because n greater than, q1 greater than, q2 greater than, etc. greater than or equal to 0 is a strictly decreasing sequence of integers. This process must eventually terminate, say at the m-1th stage, where qm-1 is equal to qmb plus am-1, 0 less than or equal to am-1 less than b, and 0 less than or equal to qm less than b, setting am is equal to qm, we obtain the representation n is equal to am b raised to m plus am minus 1 b raised to m minus 1 plus etc. plus a1 b plus a0. It remains to prove the uniqueness. Let us suppose that n has two distinct representations, say n is equal to am b raised to m plus etc. plus a1 b plus a0, which is equal to cm b raised to m plus etc. plus c1 b plus c0, with 0 less than or equal to ai less than b for each I and 0 less than or equal to cj less than b for each j. We can use the same m by simply adding terms with coefficients ai is equal to 0 or cj is equal to 0 if necessary. Subtracting the second representation from the first gives the equation 0 is equal to dm b raised to m plus etc. plus d1b plus d0, where di is equal to ai minus ci for I is equal to 0, 1, etc. m. Because the two representations for n are assumed to be different, we must have di not equal to 0 for some value of I. Take k to be the smallest subscript for which dk not equal to 0. Then 0 is equal to dm b raised to m plus etc. plus dk plus 1 b raised to k plus 1 plus dk b raised to k. And so after dividing by b raised to k, dk is equal to minus b into dm b raised to m minus k minus 1 plus etc. plus dk plus 1. This tells us that b divides dk. Now the inequalities 0 less than or equal to ak less than b and 0 less than or equal to ck less than b leads us to minus b less than ak minus ck less than b or mod dk less than b. The only way of reconciling the conditions b divides dk and mod dk less than b is to have dk is equal to 0, which is impossible. From this contradiction, we conclude that the representation of n is unique. This completes the proof. Remark: the essential features in all of the lemma is that the integers n is completely determined by the ordered array am, am minus 1, etc. a1, a0 of coefficients with the plus signs and the powers of b being superfluous. Thus, the number n is equal to am bm plus am minus 1 b raised to m minus 1 plus etc. plus a2 b square plus a1 b plus a0 may be replaced by the simpler symbol n is equal to am, am minus 1 etc. a2, a1, a0 b. Equation number 1. We call this the base b place value notation for n. Attention! The right hand side of the expression 1 is not to be interpreted as a product but only as a abbreviation for n. Remark: small values of b give rise to lengthy representation of numbers but have the advantage of requiring fewer choices for coefficients. When b is equal to 2, the resulting system of enumeration is called the binary number system. In this system, for example, the integer 123 can be written as 123 is equal to 1 into 2 raised to 6 plus 1 into 2 raised to 5 plus 1 into 2 raised to 4 plus 1 into 2 cube plus 0 into 2 square plus 1 into 2 raised to 1 plus 1 into 2 raised to 0. In the abbreviated form, 123 is equal to 111011 to the base 2. The binary system is most convenient for use in modern computing machines because binary numbers are represented by strings of zeros and ones. 0 and 1 can be expressed in the machine by a switch being either on or off. Binary exponential algorithm. Binary exponential algorithm helps in the calculation of the value of a raised to k mod n when k is large. The method is illustrated in the following example. Example 9. Calculate 5 raised to 110 mod 131. Solution. We note that in binary system 110 is equal to 64 plus 32 plus 8 plus 4 plus 2, which is equal to 110110 to the base 2. Now 5 raised to 110 is equal to 5 raised to 64 plus 32 plus 8 plus 4 plus 2, which is equal to 5 raised to 64 into 5 raised to 32 into 5 raised to 8 into 5 raised to 4 into 5 square, which is equal to 5 raised to 2 raised to 6 into 5 raised to 2 raised to 5 into 5 raised to 2 raised to 3 into 5 raised to 2 raised to 2 into 5 raised to 2 raised to 1. We obtain the power 5 raised to 2 raised to j mod 131 for 0 less than or equal to j less than or equal to 6 by repeatedly squaring while at each stage reducing each result modulo 131. Phi square congruent to 25 mod 131. 5 raised to 4 congruent to 101 mod 131. As the remainder of 625 when divided by 131 is 101. 5 raised to 8 congruent to 114 mod 131. 5 raised to 16 congruent to 27 mod 131. 5 raised to 32 congruent to 74 mod 131. 5 raised to 64 congruent to 105 mod 131. Hence, 5 raised to 110 is equal to 5 raised to 64 into 5 raised to 32 into 5 raised to 8 into 5 raised to 4 into 5 square, which is equal to 105 into 74 into 114 into 101 into 25, which is congruent to 60 mod 131 a liter. As a minor variation of the procedure, one might calculate modulo 131 the powers 5, 5 square, 5 cube, 5 raised to 6, 5 raised to 12, 5 raised to 24, 5 raised to 48, 5 raised to 96 to arrive at 5 raised to 110 is equal to 5 raised to 96 into 5 raised to 12 into 5 square, which is congruent to 41 into 117 into 25, which is congruent to 60 mod 131, which would require 2 fewer multiplications. Decimal number system. When b is equal to 10, the resulting system of numbers is called the decimal number system. Usually, we omit 10 subscript that specifies the base. For example, the simple 1583 stands for the expression 1 into 10 cube plus 5 into 10 square plus 8 into 10 raised to 1 plus 3. The integers 1, 5, 8 and 3 are called the digits of the given number. 1 being the thousands digit, 5 the hundreds digit, 8 the tens digit and 3 the units digit. In technical language, we refer to the representation of the positive integers as sums of powers of 10 with coefficients at most 9 as their decimal representation. We now derive criteria for determining whether an integer is divisible by 9 or 11 without performing the actual division. For this, we need the following results. Theorem 5. Let Px is equal to sigma k equal to 0 to m ck x raised to k be a polynomial function of x with integral coefficient ck. If a congruent to b mod n, then p of a congruent to p of b mod n. Proof. Because a congruent to b mod n, by part f of theorem 2 of the previous chapter, a raised to k is congruent to b raised to k mod n for k is equal to 0, 1, etc. m. Therefore, ck a raised to k is congruent to ck b raised to k mod n for all such k. Adding these m plus 1 congruents, we conclude that sigma k is equal to 0 to m ck a raised to k is congruent to sigma k is equal to 0 to m ck b raised to k mod n, that is p of a congruent to p of b mod n. Corollary 3. If a is a solution of px congruent to 0 mod n and a congruent to b mod n, then b is also a solution. Proof. From theorem 5, it is known that p of a is congruent to p of b mod n. Hence, if a is a solution of p of x congruent to 0 mod n, then p of b is congruent to p of a congruent to 0 mod n, making b a solution to p of x congruent to 0 mod n. The following theorem says that a positive integer is divisible by 9 if and only if the sum of the digits in its decimal representation is divisible by 9. Theorem 6. Let n is equal to am 10 raised to m plus am minus 1 10 raised to m minus 1 plus etc. plus a1 10 plus a0 be the decimal expansion of the positive integer n 0 less than or equal to ak less than 10, and let s is equal to a0 plus a1 plus etc. plus am. Then 9 divides n if and only if 9 divides s. Proof. Consider p of x is equal to sigma k is equal to 0 to m a k x raised to k, a polynomial with integral coefficient. Obviously, 10 congruent to 1 mod 9. Hence, by theorem 1, p of 10 congruent to p of 1 mod 9. But p of 10 is equal to n and p of 1 is equal to a0 plus a1 plus etc. plus am, which is equal to s. So that n congruent to s mod 9. It follows that if n congruent to 0 mod 9 and only if s congruent to 0 mod 9, that is 9 divides n if and only if 9 divides s. This completes the proof. The following theorem says that an integer is divisible by 11 if and only if the alternating sum of its digits is divisible by 11. Theorem 7. Let n is equal to am 10 raised to m plus am minus 1 10 raised to m minus 1 plus etc. plus a1 10 plus a0 be the decimal expansion of the positive integer n 0 less than or equal to ak less than 10, and let t is equal to a0 minus a1 plus a2 minus etc. plus minus 1 raised to m am. Then 11 divides n if and only if 11 divides t. Proof. Let p of x is equal to sigma k equal to 0 to m ak x raised to k. Because 10 congruent to minus 1 mod 11, we get p of 10 congruent to p of minus 1 mod 11. But p of 10 is equal to n, whereas p of minus 1 is equal to a0 minus a1 plus a2 minus etc. plus minus 1 raised to m am, which is equal to t. So that n congruent to t mod 11. The implication is that either both n and t are divisible by 11 or neither is divisible by 11. Example 10. Illustration of theorem 6 and 7. Show that the integer 15,71,724 is divisible by 99. Solution. Take n is equal to 15,71,724. The sum 1 plus 5 plus 7 plus 1 plus 7 plus 2 plus 4 is equal to 27 is divisible by 9. Hence, by theorem 6, 9 divides n. The alternating sum 4 minus 2 plus 7 minus 1 plus 7 minus 5 plus 1 is equal to 11 is divisible by 11. Hence, by theorem 7, the number is divisible by 11. Combining, the number is divisible by 9 and 11. That is, the number is divisible by 99. Now, it's time to conclude the session. In this session, first we discuss the idea of congruence and incongruence with the supporting examples and theorems. Next, we pass on to the binary representation of integers, which are convenient for use in modern computing machines. Before going to the next session, let us try to answer these questions. Find the last two digits of the number 9 raised to 9 raised to 9. Find the remainder when 4444 raised to 4444 is divided by 9. Show that 2 raised to n divides an integer n if and only if 2 raised to n divides the number made up of the last n digits of n. Hope you enjoyed this session. See you next time. Till then, take care.